Okay, so now we come to one of the main topics of this talk, which is about the cricket ball. So here is a beautiful visualization from Professor Mehta, where you see the seam of a cricket ball. So I have a picture here with me. So that's the cricket ball, and this flow going from left to right. So this here is the wake, and you can see the smoke flow visualization. So I remind you of the smooth sphere that the critical Reynolds number is about 3.5 into 10 to the 5th. Okay? But for the cricket ball, the operating range is about 10 to the 5th, which is actually way before even the curve has the left axis of my plot. Okay, so talking about cricket as such, I am sure all of you are familiar with this game. A bowler actually has the task of deceiving the batsman. Okay? So one of the ways to deceive the batsman is by speed. Okay? So if you bowl very quick, the batsman doesn't have enough reaction time, and so if you are somebody like Shoaib Akhtar, the ball comes so quickly that you don't really have much time and you deceive the batsman. That's one way. The other is actually through the lateral movement of the ball. Okay? And that I want to show you. You are, as a bowler, you have roughly 3 options available. One is the spin bowling. Okay? So you actually, the ball is spinning. Okay? It is rotating about an axis, and then the Magnus effect would become active. And we have seen this in the class, that if you have flow past a rotating cylinder, it generates a force, and likewise for a sphere as well. So that's called a drift. So the ball can actually drift in the air and therefore deceive the batsman. We are not going to talk about the Magnus effect today, so not spin bowling. The other is the seam bowling. Okay, so the seam is held vertical and the bowler hits the deck, and then the ball can actually go either of the directions, okay, to the left or to the leg side or the off side, and therefore you may get the leg or off cutters. That's because you are applying a backspin to the ball, and therefore the dynamics plays a reasonable role, but the bowler sometimes himself will not know whether the ball will go to the left or to the right. We are going to talk about the swing bowling today. Okay? This is the main topic of interest, where the bowler holds the seam of the ball at an angle to the batsman. Okay? So if you are a batsman and I am a bowler, I hold the ball so that the angle is a little bit to you. Okay? So that's what is shown here, and you could get either an in swing or an out swing, or sometimes a bowler can also do reverse swing. So we are going to first understand these definitions. So first I want to tell you what do we mean by in swing or out swing. ये इसकी डिस्टर्बेंस तो नहीं हो रही है? ठीक. So first I want to make it very clear to you the convention that at least people in aerodynamics use is, there are 2 kinds of swings. Okay, the conventional swing and a reverse swing. And a conventional swing can be in swing or out swing, and a reverse swing can also be in swing or out swing. Okay. So let's first talk about the conventional swing. In the conventional swing, the ball is always going to move in the air in the direction of the seam. So you notice I have shown a small picture here, a cartoon. The ball is always moving in the direction of seam. Okay. And the yellow one is the trajectory of an outswing for the obvious reason, and this one is kind of bowled a little bit away from wide of the crease, and it moves towards the batsman, so that's called in swing. But both are examples of conventional swing. The ball is going to move in the direction of the seam. Sometimes the batsman can be completely deceived. So if I am a batsman who holds the head steady and I can watch how the bowler is bowling at me, I look at the seam of the ball, I should be able to make out whether the ball will be an in-swing or an outswing, and depending on how the bowler releases the ball, whether it is close to the wicket or away from the wicket. But sometimes I will get deceived. I am thinking that the ball is going to move like this because this is the direction of the seam, but in fact the ball goes the other way. So that's what we are going to call as reverse swing. Okay, so I hope the difference between the conventional swing, which I will simply call as swing, versus reverse swing is clear. Okay. So if I am a batsman, then I can see from the action of the bowler how the ball orientation is going to affect me. So it is shown here that if I am a right-handed batsman and the bowler is bowling at me, so there are these bowlers coming at you, then if the seam is held straight, this would be no swing, this would be outswing, and this would be in swing. Okay. Okay, now we look at the aerodynamics of how this is achieved in a flow. So again, this is a picture taken from Professor Mehta's experiment, a smoke flow visualization. The flow is from left to right, and what you see here is the seam of a cricket ball, and the flow on the lower side actually hits the seam hits the flow early than the upper side. So this becomes turbulent and it stays attached for a longer duration. But if you look at the flow on the upper side, which is the non-seam side, then it actually the flow separates even before it hits the seam, and that's where we get a laminar separation, and this one we get a turbulent separation, and therefore you would see a suction on the lower surface of the ball, and there would be a force acting in this direction and the ball will move in that direction. So this is the conventional swing. Okay, we did lot of experiments at the National Wind Tunnel facility. Okay, so this is a closed circuit wind tunnel. There is a fan here which drives the flow, and this building here inside has a test section. I will show you a picture of that. So you can just imagine there is a room in which there is a flow, and we keep this model and we can measure forces. So here is again the schematic of the wind tunnel. So that's the flow direction. Okay, the fan drives the flow. This is the test section, and there is a picture inside the test section. So we have taken a cricket ball and mounted it on a support. So that's called a sting support, and there is a balance embedded inside this sting. So it's a 6-component balance. It can measure 3 forces and 3 moments. So we can orient the ball at different seam angles. We can change the flow speed u infinity, and then we can measure the forces, and we can get data of how the force change with speed and with different seam angles. So I am going to show you that. It's a very quiet tunnel. The maximum speed in the tunnel is about 80 meter per second. That actually is more than enough that we need. 80 translates to about 300 kilometers per hour, so way more than any bowler can go. And it has extremely low free stream turbulence level. So that means the flow is extremely quiet. So it is a very quiet flow when it approaches the ball, and then the seam of the ball, if it makes the flow turbulent, it would be very easy to detect. Mind you, if I had a very noisy wind tunnel where the flow was already turbulent when it comes to the ball, then I will not be able to study what the seam does to the cricket ball. Very quickly we realized when we did these experiments that because these balls are handmade, the repeatability of the experiments is very poor. Okay, so if I do one experiment on one cricket ball, then I do an experiment on another cricket ball, the match between them is not up to the mark. So we decided, in addition to using cricket balls, we will also make some synthetic balls. So using 3D printing, we made these plastic spheres with seam on them. So this is an example of a seam which looks exactly like a cricket ball, and this one more like a single seam to give us just a study of what the seam does. And then we can adjust the diameters so that we can get the desired Reynolds number in our wind tunnel. This here shows the setup for the force measurements on an actual cricket ball. So you see a few pictures here. For example, this picture shows us the flow goes from right to left, and you can see there is a cricket ball here, and I told you there is a force balance which is embedded in this sting, and it can actually tell us what the force on the cricket ball is. Here's a top view which is extremely educational. So you can see this is how the seam is oriented. So we can replace the model with a different seam angle and then do experiments for different seam angles. We can also do pressure measurements. Okay, so if you want to measure pressure on the surface of the cricket ball, so what we do is we take a cricket ball, make small pressure ports on it, and then the pressure scanners can be put inside the hollow cricket ball, and then that can be also used to look at the flow. In fact, this is a picture of how the pressure ports are drilled onto the model. So they are done very carefully. So this is the flow direction, and there are different splines that we choose, and we can get data on these different points. We also carried out something called a PIV, okay, particle image velocimetry. This is a very interesting technique, non-intrusive. So what you see here is a model of a cricket ball which is fixed inside the wind tunnel, and then we shoot a laser, a sheet of laser, okay, and that illuminates a certain section of this cricket ball. So we have to illuminate it twice, once from this side and once from the back side of the wind tunnel. And what we do is we fog the tunnel with smoke particles, okay, and we take two pictures. So we flash the laser twice within a very short time interval. So we take one picture where we can take all the locations of these fog particles, and then after a very small interval the laser shines again, we get a second picture, and because these fog particles are of different diameters, we have a software which correlates. So we are able to locate one fog particle has moved to what new location, and because we know the delta x, delta y and delta z which the particles have moved, and we also know the time difference between the two shoots of the laser, we can actually estimate the velocity of the fluid particles. Okay, so it's a very interesting technique. So that has also been used to study the flow. Okay, first the convention. So the flow is going into the screen of the computer or your mobile phone, wherever you are watching, and that's the seam orientation. The lift is in the vertical direction. We are not so much interested in that. We are interested in the side force because that gives the lateral movement of the ball. So the primary seam and then the secondary seam is also shown. So if I get a force in this direction, in the direction of the seam, that's the conventional swing force, and if I get a force in the other direction, that would be reverse swing, as the name suggests, okay, and therefore the ball would reverse if I get force in the other direction. Some results. So on the x axis is the Reynolds number, and on the y axis are the force coefficients. There are three force coefficients plotted here, and I would like you to pay attention to two of them. The drag force, which is in red circles, and then we are also going to look at the blue diamonds, which is actually the swing force or the swing force coefficients. So first let us look at the swing force. So the blue diamonds, as you see, they tell us of the coefficient of swing force, okay. Notice that up to a Reynolds number of roughly 1.9 into 10 to the 5th, the blue diamonds show a positive value of roughly 0.3 or 0.35, and then suddenly they show a negative value. So this is the region of reverse swing, and the white colored region is the region of conventional swing. Okay. Look at the drag. So the drag is reasonably large in the conventional swing, and then here the transition takes place and you get a massive reduction in the drag coefficient because the boundary layer has become turbulent. Schematically, so this is the picture for the conventional swing. So the flow is going from left to right. We will call this upper surface as the seam side, the lower surface on the non-seam side. On the lower surface, the boundary layer is laminar, so you get a laminar separation close to the shoulder. On the upper surface, because the flow goes over the seam, the boundary layer becomes turbulent early. If there was no seam, then this boundary layer would also be laminar, but it has been disturbed by the seam, the roughness, and therefore it becomes turbulent, and therefore it separates at a much more downstream location. Okay. So you get turbulent separation on the upper surface, laminar separation on the lower surface, thereby you get more suction on the upper surface, and there is a force in the lateral direction that gives rise to swing. Let us look at what happens in the case of reverse swing. This boundary layer was already turbulent, we have seen it. Now by that time, when you increase the speed, the boundary layer on the lower surface also goes through a natural transition, so it becomes turbulent, but because this is a natural transition and the one on the upper surface is a forced transition, there is some difference in the turbulence level. In fact, people have observed, and we have observed in our experiments, that when you get a natural transition, you get a large suction, but if you have a forced transition, then there are some losses next to the seam, and therefore the suction that you get is not as much as you would see in a natural transition. So now what has happened, that this force is a little bit, this pressure here is much lower than the pressure you would see on the seam side, okay, because this is a forced transition and on the lower surface it is a natural transition. And that is why now overall you get a reverse swing, a force in the other direction. So as far as a bowler is concerned, what he would see is up to a certain speed of the ball, a certain delivery speed, he is able to swing the ball. If he exceeds that critical speed, he is able to reverse swing the cricket ball. And these experiments are with a brand new cricket ball. Okay, so what these show is that you should be able to reverse swing a brand new cricket ball. Okay, so it's a myth that you cannot reverse swing a new cricket ball. In fact, if you watch TV carefully, you will be able to see that many bowlers who can deliver at a very high speed, they are able to get reverse swing even with a new cricket ball. An interesting aspect is that the coefficient of swing is much larger than the coefficient of reverse swing. You can see this goes up to almost 0.3 or 0.35, whereas this one does not even touch a negative 0.2. So in general, the coefficient of reverse swing is going to be smaller than the coefficient of swing. But don't worry, the force is proportional to u squared. So when you are reverse swinging, the speed is much larger. So u square here is going to be much larger than the u square in the swing, and therefore it kind of makes up. What happens if we replace the ball with the models, okay, the synthetic? So what this picture shows is the coefficient of drag and the swing coefficient with Reynolds number. Let me take you through the different curves. So the blue curve is the cricket ball that we have already seen. So this was shown in the last picture. The one in the green is actually a synthetic cricket ball made out of plastic, and the surface is very smooth. So because it has a smooth surface, So the transition takes place at a higher speed, okay, and as expected, the swing, actually if you look at the green curve, it swings up to a much higher speed, and the reverse swing takes place probably beyond what a bowler would be able to achieve. If you have a single trip, then it moves further at even a larger speed as expected, and there is some difference between if you have roughness because of pressure ports, then the curve becomes a little bit smoother. So qualitatively, all balls behave the same, whether they are real cricket balls or they are synthetic balls, but just the location of the critical speed changes. So I want to bring your attention to the effect of weather, okay, to explain you the phenomenology for how a bowler would interpret these curves. So imagine I am a bowler who is going to do my activity either in Eden Gardens or in Lord's, London. Okay. So the temperature at Eden Gardens is something like 35 degrees centigrade, whereas in Lord's, let's say it is winter, it is about 15 degrees centigrade. So that would change the viscosity of the air. So you can see this at Kolkata, it is higher, and it's a little bit lower at Lord's. Suppose I am a bowler like Ganguly, okay, a gentle seam bowler, 80 kilometers per hour. If I bowl in Kolkata, my Reynolds number is something like 0.8 into 10 to the 5th. Okay. So if I look on this curve, I am somewhere over here, 0.8 into 10 to the 5th. So I will generate a little bit of seam movement. Same bowler, same speed, but I am in England now, and my Reynolds number, because of this viscosity change, is now higher. It's about 1 into 10 to the 5th. So I move, so there is a substantial increase now in my Reynolds number, and therefore I get higher swing force. So I am going to generate more seam movement in Lord's as compared to I am in Eden Gardens, everything else remaining the same. What happens to somebody like Bumrah? Bumrah bowls at 145 kilometers per hour, let's say, and he generates a Reynolds number of 1.5 into 10 to the 5th. So that would lie somewhere here. So he is able to swing the cricket ball at 145 kilometers per hour for a seam angle of 30 degrees. Everything remains the same, but he bowls at Lord's. Now he generates a roughly 2 into 10 to the 5th. You see, now he is able to reverse swing. So the weather conditions, the humidity conditions, the temperature conditions, they can make enormous difference. Okay? So the fluid mechanics can actually help you understand all this. So rather than looking at experiments of speed versus force, it is more efficient to plot them with coefficients versus Reynolds number, and then you can back calculate and take effect of the weather. Alright, now some flow visualizations, that what exactly is going on. So we use the same techniques now for the cricket ball. This is the cricket ball with 5 trips, and these are different speeds, different Reynolds number, probably a little bit difficult for you to see. So I have drawn a schematic here. Okay. Now the laminar separation bubble, which was axisymmetric in nature for a sphere, takes a very interesting shape for a cricket ball. So let's look at a very low Reynolds number. Here you get no swing, the seam pretty much plays no role. The boundary layer is laminar separation on the non-seam side, it is a laminar separation on the seam side. Increase the Reynolds number and you get this laminar separation bubble. So the seam is able to make the boundary layer turbulent near these polar regions, but if you look on this upper side, you get a big structure here, which is the laminar separation bubble, and it starts shrinking in size as you increase the Reynolds number. So at a reasonably high Reynolds number, actually the flow has become completely turbulent on the upper surface, and you can see there is no oil there as a evidence of that there is no laminar separation bubble. If you increase the speed even further, now on the lower surface you are going to get a laminar separation bubble. So in all these pictures you can see that there is a laminar separation on the lower surface. However, if you do experiments with this one trip, you are able to see some pictures of reverse swing also. So let me take you through them. So this is an example of conventional swing, wherein on the upper surface you see a laminar separation bubble, and on the lower surface, so this is the seam side, this is the non-seam side, and on the non-seam side you see there is a laminar separation. But when you increase the Reynolds number to roughly 1.7 into 10 to the 5th, then you start seeing a laminar separation bubble even on the non-seam side. It has become turbulent. So let me explain you the phenomenology. X-axis is Reynolds number, y-axis is essentially the coefficient of drag and the swing force. For very low Reynolds number, seam does not make a difference and I get no swing. So that's the blue region. So no swing, laminar separation on the top, laminar separation on the bottom. In this region of conventional swing, you get a laminar separation bubble on the seam side. Okay, so the boundary layer undergoes a turbulent separation eventually, but there is a laminar separation on the lower side. So there is a net low pressure on the seam side of the ball and you get a positive CZ. So that's the swing. Increase the Reynolds number further, then you get an early turbulent separation, because this, as we saw, the laminar separation bubble shrinks, so this turbulent separation also moves upstream. But then there is a laminar separation bubble on the lower side. Okay, so you get a delayed turbulent separation on the lower side, and now you get a force on the non-seam side and you get reverse swing as shown here.